We're going to continue our mechanism exploration using a mechanism you are not responsible for. That means you don't have to learn how to give me the arrows for ozonolysis. You do not have to learn the ozonolysis mechanism. What we have here is all the steps, but I took two different molecules, so I couldn't give the answers away by having this product be what I start with in the next step, because I would give the answers away. So two separate reactions are going on. You don't even need to know that. And what's going on? It looks like these were connected and I just didn't copy the whole thing. Let's look at my stamp. Yeah, I missed that. You didn't get one? Wrong one. Here you go. So there's a few corrections. Please fix this. Oh, wow. Fix this, please. They should be connected over there. And I forgot to give the arrows for the last one. So I'm going to give you the arrows. They should be on the question already. They are not. Oh, don't straighten things for me, please. That arrow leads to this arrow, leads to this arrow, leads to this arrow. Doing it that way, though, you're led to believe that two arrows are coming together. And the bottom, it looks exactly like that. That never happens. So I want it to be clear the two arrows are not coming together. The first arrow is what causes the second arrow, is what causes the third arrow. And the fourth arrow doesn't know that arrow one happened already. It's just going to become a lone pair on that O. All right. And this is an exercise in, do you know what curved arrows mean? And that's very important. And it says, where it says stereo, you will need to use wedges and or dashes to indicate stereochemistry. For example, these bonds are happening at the same time. So when you draw the bonds off the ring, talk to me about wedges and dashes. Anybody want to talk about it? When they happen at the same time, that's called thin stereoselectivity. So what do you want me to draw for that? The two choices are wedge, wedge, or wedge dash. Wedge, wedge, because they're happening at the same time. You can't both be on top of the molecule and underneath the molecule at the same time, can you? Nobody can be in the same place, two different locations at the same time. So there is one of the bonds. Here is the other new bond. And what are they each connected to? Oh. In fact, I'm going to add this to my question too. Normally, I don't ask you to show all lone pairs, but it's a good exercise. All right, now talk to me. You used to have two bonds between the first O and the second O. What are you going to have when you're done? One bond. The second bond became a lone pair. Don't forget the middle O we haven't drawn yet. Single bond. And down here, we didn't touch this bond. And talk to me about lone pairs. How are you an O minus? How many lone pairs does this thing really have? There's only one answer. And if I don't get the right answer, I will stop writing a single lone pair because I only need one lone pair. And I will draw every lone pair. If you do not know what makes an O minus, I need to know how many bonds it has and how many lone pairs, and I need it now. 3 lone pairs for an O minus and 1 bond. Okay, now you just used one of the lone pairs in the mechanism. Do you agree? It's right there. How many are left? She said I started with 3 lone pairs. How many are left? 2. Put them on. Now, when you're a cation and an oxygen, you have 3 bonds and 1 lone pair. Okay? I didn't show the lone pair because I didn't need to. Now, you started with a lone pair. I can draw it there if you want. There, it was there from the beginning. I'm going to erase it, but I know it was there. Now, you're putting a second lone pair on this oxygen, correct? So please draw 2 lone pairs on that oxygen as well. Good. Top oxygen. That's normal oxygen to start with, right? It had 2 bonds and how many lone pairs? Normal oxygen with no formal charge has 2 bonds and how many lone pairs? 2 lone pairs. I didn't change the number of lone pairs. I made a sigma bond and I broke a pi. I didn't add or subtract lone pairs. 2 stays 2. Got it? So one of the reasons this reaction happens is I got rid of all my formal charges, right? Everything's neutral. It's got a lot of lone pair repulsions though, doesn't it? Now you see what I was talking about earlier? See, this intermediate looks a lot like this one. They just have different carbon skeletons attached. So I'm showing the next step of ozonolysis with a different molecule. So here's your lysis, right? That's a cut. You're going to have a piece with 2 carbons and a piece with 3 carbons. So which of these pieces has 2 carbons, the bottom or the top? When you're done, which one has 2 pieces, the top or the bottom? 1, 2, double bond to O, 2 carbons. Now that O, how many lone pairs? It's neutral. Started neutral, it's going to end neutral. 2, 3 carbons is the one on top. Single bond to O, single bond to O. Now the bottom one used to be neutral, which means it had these 2 lone pairs to start with. And the top one used to be neutral. It had these 2 lone pairs to start with. The bottom one's getting a new lone pair. Is it clear that this arrow is becoming a lone pair on the bottom oxygen? Right there. Is that clear? So it gets a 3rd lone pair. And what kind of formal charge does that oxygen have? Negative. That's an oxide. What about the carbon? It only has 3 bonds now. It used to have 4. Plus. You're saying, wow, that's terrible. It's a carbocation. I say, yes, it's terrible, but it's not as terrible as you think because this thing's doing this. What's that? Moving arrows inside of a molecule without changing the formula or anything. What do you call that? It's an arrow with 2 heads. 1 arrow with 2 heads. What do you call that? Resonance. This one's going to be a better resonance form because it has complete blank blanks. What am I talking about? Just blank. This one had an OV on the left. It doesn't have an OV on the right. What's that mean? Uh-oh. I'm sure there's a few people in this room right now who have a test that has the comment OV on it and the worst comment -1 beside it. What does OV stand for? Octet violation right here, right? I wanted to hear that. I didn't hear it. Octet violation. Yeah. No octet violations. That's why it's better. Comment. No octet violation. OV. There you go. Yeah. Next one. Next one's the coolest one of all. Well, the carbon skeleton didn't move. No arrows from the carbon skeleton. So ding, 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 ding to a 5. Yeah. And talk to me about these bonds to O. You used to have 2 bonds to O. Now how many bonds from C to O when you're done? This C to this O. 1. That O is also ending up hooked up to what carbon? The pi breaks and becomes a sigma to this carbon on top. This carbon still bonded to this oxygen with 1 bond. That carbon still bonded to the oxygen above with 1 bond. No change. O minus ended up attached to that. I believe every oxygen should be normal now, so talk to me about lone pairs. 2 lone pairs each. 2 sigma bonds, 2 lone pairs. Yep. These 2 boxes look like the bonus question from our previous activity, huh? A little bit? They were bonus. They still are. All right. The big finish. You want to start with a sulfur just for fun? And show all lone pairs. So sulfur has 2 CH3s. And you do know that sulfur, like oxygen, started with 2 lone pairs. There's I put them on there. When you use one of them for a bond, so you still have 1. And the new bond is to an O. And that O had 2 lone pairs. Just a reminder, I'm going to put them on, why not? What about that O on the bottom right? It had 2 lone pairs. We made the new sigma bond, but what about this 4th arrow? What's it becoming? A lone pair. So how many lone pairs when you're done? There's lone pair number 1. There's lone pair number 2. I didn't touch them. I need 3. That's how it became an O with what charge? Negative. And sulfur's in the oxygen family. What do you look at when you see a sulfur that has 1 lone pair and 3 bonds? Plus, and when it was oxygen, we had a name for that. O with a plus was oxonium, right? What are you going to call sulfur with a plus? I just want to hear you say it. Well, say it. Sulfonium. That's right. Yeah, charges may apply. No, not that sulfonium. No, sulfonium. Yeah. Okay. All right, 2 carbons is the bottom part, right? These are the 2 carbons that stay intact. There's a carbonyl here. There's no more bond there. Oh, it's a piece of cake, isn't it? Hey, it's the same as it was before. So that molecule appeared twice in the mechanism. Look at that. And 3 carbons up top, double bond to O. And talk to me about how many lone pairs on that O. 2, yeah. Ketone. Doesn't it follow the predictive pattern of erase the pi and put O on each side? Isn't that the two boxes, the two first boxes? Yep. And that's what happens to sulfur over there. So. And I guess this thing would break down to being an aldehyde here and a ketone down here, but it wasn't even asked. Hey, what about a better resonance form for this? Oh, I think we can get rid of the charges. Always flow away from minus towards plus. I hope that makes sense. These are electrons, right? And you're going to say, wait, Dr. Whitaker, you can't do that. Sulfur's got an octet violation. You're going to get an OV minus 1. Oh, no, maybe you want to reconsider. And I say, oh, no, no, I don't want to reconsider. Sulfur can violate the octet rule. It's in row 3, right? You can go beyond the octet as long as you're beyond row 2, because the 3D orbitals are now available to make more bonds. There you go. So yeah, that's dimethyl sulfoxide now. Dimethyl sulfoxide. And then we had the sulfur, it was called dimethyl sulfide. Makes sense. Sulfide becomes sulfoxide. Someday we're going to see these initials again. DMSO. And this one's just DMS. Yeah. DMSO is a solvent that's used for a lot of things, including drug delivery. Interesting. And that's all we have for the ozonolysis today.